Yeah, you assume the change is negligible. So one thing we could have done is, if I didn't want to do the quadratic, I might have tried this. I might have said x is much smaller than 0.1. If x is much smaller than 0.1, then we'll get x squared over 0.1, which means that x is equal to 0.1 times 2.13 times 10 to the minus 4. So that would be 2.13 times 10 to the minus 5, and take the square root of that. 2.13 times 10 to the minus 5, square root of that. 0.00416. 0.00461. 0.0461 is 0.1. So this 0.1, the percent change is going to be 0.00461 over 0.100. So this would be a 4.61% change. Now, a 4.61% change, is that okay?
It's okay.
It's not good, but it's okay. This is acceptable. But since the math is not difficult, you know, since the percent change is so high, I would not do this. I'd just go ahead and do the quadratic here. If you have a quadratic calculator. If you don't have a quadratic calculator, then of course, solving the quadratic is a pain. Does somebody have a quadratic calculator? Can you punch it in? Oops, sorry. Can you punch it in? You did? Thank you. Okay, so you got x is equal to?
0.00. It was 45099.
Like this? Okay, 00 45099. Okay.
And the other one was a negative one. So
Yeah,
negative.
that one doesn't work. Okay, so this way we don't have to use the simplifying assumptions. Let's run with the audio here. And so that means the carbonate comes out to 0.1. We'll carry some extra zeros here. Minus, look at the difference here. You know, we calculated 0.00461 using the simplifying assumption. Here we get 450 without using the assumption. So the error introduced here is kind of significant, I think. Like a 2% error. So anyway, going back over here, this is going to be 0.0045. We'll just go 450. We'll just carry one extra digit because already we're subject to round off. So this is going to come out to 0.9. What is it? 0.9955 molar. 0.9955 molar. Did we lose much? Actually, no. This is wrong. I missed it. I screwed this up. 0.09. 0.0955. So we lost about 4.5%. This is a weak base. Weak base is only partially hydrolyzed water. Carbonate's a weak base. And this is going to be 0.045 molar and 0.00450 molar. Now, this is a bit tricky. This problem is a bit tricky because this is a dibasic base. And so, you know, carbonate picks up one proton and goes to bicarbonate, but it can also pick up a second proton and go all the way to carbonic acid. And so, this is what we're going to do. For all these problems. We look for all the contributors. And so in an acid solution, we look for all the hydronium ion contributors. If you look at the HCl calculation we did yesterday, the hydronium ion contributors were two. We had HCl and we had water. It turned out water contributed over 90%, around 90% of the hydronium. HCl contributed about 10% of the hydronium to the total solution. And so whenever we have acid in water, we look for all the hydronium ion contributors. When we have base in water, we look for all the hydroxide ion contributors. And it turns out that we're not done with this problem yet. We're not done because we have a potential, two more potential contributors. The two more potential contributors are these. Bicarbonate. We formed some bicarbonate. And so bicarbonate can contribute additional hydroxide to this solution. And so if we go bicarbonate plus water gives us carbonic acid and hydroxide. But bicarbonate's an interesting species because bicarbonate we know is amphoteric. And what an amphoteric species can do is it can hydrolyze either way. And so bicarbonate can collide with the water to form hydroxide, and bicarbonate can collide with water to form hydronium. Because if bicarbonate collides with water, and in this case it loses the proton rather than gains a proton, then we'll form hydronium and carbonate. And so that's because bicarbonate's amphoteric. And so amphoteric species hydrolyze both ways. And so does it cancel each other out? Like say, for example, this one produces hydroxide, the other one produces hydronium. It cancels each other out for water. Water is amphoteric. In fact, Kw for water is both Ka and Kb. You know, if you look at water, water is perfectly amphoteric. Because water can hydrolyze water in a Ka to produce hydronium. Water can also hydrolyze water in a Kb to produce hydroxide. Well, actually, it does both at the same time. We call it Kw. And so Kw is both hydrolysis of water to produce hydronium and hydrolysis of water to produce hydroxide. And water is perfectly amphoteric. You know, it's like a 50-50 fluid. And in other words, we're going to produce just as much hydronium as hydroxide. So it's not biased one way or another. But most amphoteric species are biased. That is, most amphoteric species are going to prefer to be basic, or they're going to prefer to be acidic. In other words, they're going to generate different amounts of hydronium and hydroxide because they don't, you know, both of these reactions aren't equally probable. And so here, in this case, it gets tricky because, wait a minute, should we do, maybe we need to do both. Maybe we need to do the Kb for bicarbonate and the Ka for bicarbonate, and then just figure out how they cancel. You know, let's see which one produces more hydroxide, which one produces more hydronium, and then figure it out, right? But it gets even more complex because when we look at bicarbonate, do you see something here? What I see is this. If I look at bicarbonate in the Ka sense, I see the equilibrium between bicarbonate and carbonate in terms of pH. And so here, this is bicarbonate and carbonate in terms of pH, the power of the hydronium. But take a look at our original equilibrium. Our original equilibrium is the equilibrium between carbonate and bicarbonate in terms of pOH. Now, the thing that happens here is if the pH or the pOH changes, you know, it's going to impact each other. So for example, if the pOH goes up, the pH must go down. Or if the pH goes up, the pOH must go down. And so the pH and the pOH are in the seesaw relationship. And so what we see here is this is redundant. We already did this equilibrium. This is redundant because this just describes the equilibrium we just did. The only difference is we calculate the pH in this case. In that case, we calculate the pOH, but this is the same equilibrium. And so this is what we call redundant. And therefore, we come up with a rule. The rule is in base solutions, we only look at the hydroxide producers, because all the hydronium ion producers will be redundant. In acid solutions, we only look for the hydronium ion producers, and we ignore all the hydroxide ion producers, because this is what's going to happen. We're going to have multiple equilibria, and the multiple equilibria are going to get quite complicated. And so what we say here is we've generated this. We generated this species, and this species itself can produce hydroxide. So what we'll do is we'll carry it over here, and we'll get 00450 molar initial. And then what we're going to figure out is how much additional hydroxide will this species that we just made produce. And so here it's going to be minus X, plus X molar, etc. And we need the Kb for this species. Now the Kb for bicarbonate is going to equal, Kb for bicarbonate equals Kw over the Ka for what acid? It would be the Ka for carbonic acid. And so this is 1.0 times 10 to the minus 14. The Ka for carbonic acid is 4.4 times 10 to the minus 7. I wrote that out on the board earlier. And therefore the Kb for bicarbonate is what? Well, why don't you go ahead and work on solving this problem? Okay, we did the first one. Try the second ice table here. Do you know we have a third ice table? Do you know what the third ice table is going to come from? If we're looking for all the hydroxide ion producers, then carbonate's one, and then we form some bicarbonate. Well, bicarbonate's another one, and then, well, we form carbonic. Does carbonic acid, is that amphoteric too? Does that produce any hydro? No. And so what's the third ice table going to be? There's one more hydroxide ion contributor to this solution. You got it? Water, right. And so we're not done yet. We're in the middle. And so go ahead and do this calculation, and then we've got one more to do after this. That's because this is a more complicated. This is dibasic base. If we had a monobasic base, then we would have just had this, the Kb and Kw, water. Those would be the two hydroxide ion interests. With a dibasic base, we're going to have what we call Kb1, Kb2, and Kw. With a tribasic base, we'd have Kb1, Kb2, Kb3, and Kw. That's 4 ice tables. The same thing goes with acids. If we had a monoprotic acid, it would be Ka and Kw. A diprotic acid would be Ka1, Ka2, and Kw, 3 ice tables. A triprotic acid, Ka1, Ka2, Ka3, and Kw. Those would be all the hydronium ion contributors in solution.